between particularly Faraday's law and Ampere's law, and now I have to introduce another brilliant insight of Maxwell's. Maxwell said, look, changing magnetic fields give rise to electric fields. That's what Faraday tells us. Changing electric fields give rise to magnetic fields. That's what Maxwell told us when he modified Ampere's law, sometimes called the Maxwell-Ampere law for that reason, or the Ampere-Maxwell law. There's a new possibility, Maxwell realizes, a kind of self-replicating electromagnetic structure propagating through empty space as each changing field gives rise to the other. Now, it's not essential that a changing magnetic field make a changing electric field, but unless the changing magnetic field is changing uniformly, and that's impossible really because it would just have to keep growing and growing and growing, then the electric field that gets induced is going to be changing, and it will give rise to magnetic fields that will also be changing. So this possibility of each kind of field generating the other comes up. We could look at it symbolic like this. Change in electric field gives rise to a magnetic field, which itself is likely to be changing, and the change in the magnetic field gives rise to an electric field, and that process repeats itself, that electric field changes, and we get the self-replicating structure propagating through space and carrying with it electric and magnetic fields that are continually regenerating each other. That structure is called an electromagnetic wave. So Maxwell's insight was that there would be these things called electromagnetic waves, and he was able to argue from his equations that this ought to happen, and he was able to calculate from his equations what the properties of these waves would be. And a calculus-based introductory physics course can get far enough to actually do those calculations. We won't do them here, but I will show you the results because they are profound and important. Electromagnetic waves in vacuum, it turns out, look something like this picture. The electric and magnetic fields turn out to be perpendicular to each other, and they're also perpendicular to the direction the wave is going, and that means these are transverse waves like we talked about way back in lecture 18. These are transverse waves. They're waves analogous to waves I set up on a vibrating string that were vibrating at right angles to the direction the wave was going. Electromagnetic waves in vacuum. And here you see a kind of movie, a symbolic movie showing some electric and magnetic field vectors showing sort of what a wave looks like and how it propagates. And the electric and magnetic fields, notice, also are in phase. That means their peaks occur at the same point in time, and they go through zero at the same point in time. So we have electric and magnetic fields at right angles to each other and at right angles to the direction the wave is moving, and the electric and magnetic fields are in phase. How fast do these waves go? That's an important question. The wave speed is determined by Faraday's and Ampere's laws, which are making this continually self-replicating electromagnetic structure. And without going into the mathematical details, the only thing in there that could determine a speed are these constants. The magnetic constant mu naught and the electric constant k. Now let me back up a minute and talk about those constants, because they came from experiments done in the 18th and 19th centuries on simple things like static electricity and magnets and current carrying wires and the forces they produce, stuff that has nothing to do with waves. And yet, those two constants appear in these equations in a way that determines the wave speed. In fact, the constant mu naught over 4 pi k, that combination, turns out to be the 1 over the wave speed squared, and that's what the mathematics tells us that we won't work with. So the wave speed, the speed of an electromagnetic wave in vacuum, not somewhere else, is the square root of 4 pi k over mu naught, and that's important enough that we're going to do the numbers. 4 pi, 9 times 10 to the 9, mu naught is 4 pi times 10 to the minus 7, the 4 pi's cancel. We've got the square root of 9 times 10 to the 16 when I take 10 to the 9 and divide it by tiny little 10 to the minus 7. This is all in SI units, so it's going to come out in meters per second. Take the square root of 9, you get 3. Take the square root of 16, you get 8. 3 times 10 to the 8th meters per second. Now, you may have heard that number before. It's a big, fast speed. But it's a known speed. It was a speed that had been known for a couple centuries before Maxwell's time. It is the known speed of light. And Maxwell immediately realized he had discovered what light was. He had discovered that light was an electromagnetic wave. He had suddenly brought the whole science of optics under the umbrella of electromagnetism. That is a brilliant synthesis, one of the crowning intellectual achievements in the history of science. The recognition that light is an electromagnetic wave, because light travels at the speed 3 times 10 to the 8 meters per second, and indeed it can consist of these electric and magnetic fields. So let's look a bit more at electromagnetic waves, their history and their properties. So a brief history of electromagnetic waves. So we go back to Young in 1801, who did interference experiments that showed that light was a wave. Newton had believed it was a particle. Young